we talked about how this book, the effect this book had on mathematics, but even humanity, until apparently until the 20th century. And I don't know, maybe this, I don't think it continues to be the case, but this was the second most published book of all time, second to the Bible. So it's gone through, of course, Euclid wrote this in roughly, 350, 300. Yeah. So this, we'll just call it 300 BC. Euclid is working in what city? Alexandria. So this is in Alexandria, in North Africa, in Egypt. And let's talk about the structure a little bit. Let me try to make it legible. So I'll write. The structure is it has 13 books. So let me show you, please. Okay. Here's Euclid's Elements. I will add a link to this. You can't see that. Okay, here's Euclid's Elements. I'll add a link. In fact, there already is a link, but I'll add it again to the 13 books of Euclid's Elements. So it's 13 books in total. Let's get a global overview before we start zooming in. We're going to go through book 1 in quite some detail, and then we'll touch a few of the other books. Book 2. So book 1, let's talk about book 1. Book 1 has 48 propositions. Here, let's have a look at book 1. We're going to go into detail. It has 23 definitions, 5 postulates, 5 common notions, 48 propositions. Propositions are the theorems, the facts that are not obvious. So 48 propositions. Do you know what each of these books is meant to culminate in something amazing? So what does book 1 culminate in? Take a wild guess. The Pythagorean theorem. The Pythagorean theorem. In fact, proposition, they're called I-47, meaning book 1, proposition 47, is the Pythagorean theorem. But I said there are 48 propositions. So what's I-48? Yes, the converse. Very good. The converse to the Pythagorean theorem. Here's how devoted Euclid was to getting the Pythagorean theorem in this book 1. So book 1 is like introduction to geometry. Okay. Let's call this intro to geometry, getting everything set up. It had 48 propositions. What's proposition 46? Just if you were to guess, what's the one thing you need for the Pythagorean theorem? You're given a right triangle. Remember, the Pythagorean theorem is about sums of areas, not sums of squares of side lengths in this version. So in order to get an area, so it could be, and later on it is, but when you just start with a right triangle, Euclid's going to construct actual squares on those side lengths, as you'll see. And so I-46 is, how do you actually construct a square? Constructing a square on a length. So someone gives you a length. Can you construct a square on that length? It takes him 46 propositions to build up to the construction of a square. The thing that we do, like not for real, since we're not doing it completely rigorously, he wants to do it completely rigorously. And he realizes that in order to do it completely rigorously and prove everything that he wants to prove about a square, it takes him 46 propositions. What does he start the chapter with? I-1, which we'll go through in detail in just a minute. I-46 builds up to a square so that I-47, he can prove the Pythagorean theorem. I-48, he proves the converse to the Pythagorean theorem, and he's done with book 1. He starts the very first thing. He ends with nearly constructing a square. The first thing he does is, that's the first definition. Very good. Yeah, he defines what it means but to construct a point doesn't take anything. There's like the first thing that you would want to do. He constructs a square at the end. At the beginning, he constructs, circle is also an axiom that you can construct a circle. but he constructs a triangle, an equilateral triangle, constructs an equilateral triangle. To see why people love these books so much, you really have to like see not just go proposition by proposition and prove everything. It's like looking at a piece of music and saying, oh, look at this measure. This is a very interesting measure. Like, no, it's not. It's the entire work. It's the adagio followed by the allegro, like the structure, the pieces, the themes that are coming back and forth. It's really a masterful piece of work of logic, in the same way as a great work of art. Okay, so we're going to spend quite a bit of time on book one. Let's just get an overview of the elements themselves before we go any further. Book two is devoted to geometric algebra. You can read the entire all the books yourselves, but something that maybe I'll put quotes: geometric algebra. So these are things like when you write a plus b squared, of course, none of this kind of notation, none of this algebra exists for another 1,000 years. But you guys know that a plus b squared is a squared plus 2ab plus b squared. The way Euclid would say this geometrically, please, is if I have an a plus b square, meaning by a plus b, then if I make a square out of the length a added onto the length b, then that's the same as an a by a part and a b by b part, and then an a by b part and another a by b part, right? So that's the kind of thing that's being understood in book two. Book three goes into circles, tangents. So book three is circles, like what today might be called competition math, high school competition math, tangents, secants, all kinds of great constructions. Like if I give you a circle, but I just drew the circle with the compass, but I forgot to put a point where the center was. Can you figure out where the center was? Find the center, etc. There's a long, we're not going to go, we could spend an entire semester just going through, and people should in high school spend an entire year going through these books in some detail. Book four, the culmination of book four is constructing regular n-gons. So book one, he constructs a regular 3-gon, equilateral triangle. Beginning, at the end, he constructs a regular 4-gon, a square, equilateral square. So regular polygons, regular n-gons. He constructs the 15-gon. Construct again with straight edge and compass, you can make a perfect 15-gon. And it's an amazing construction. We're not going to go over it, but we will spend a little bit of time talking about that because it relates very much to Gauss and constructibility in general. Book five is about ratios and proportion. Book five is about ratio and proportion. Things like if A over B is equal to C over D, then that's the same thing as A times D is equal to B times C. Things that to modern ears don't take all that much work. We know how to cross, because we have algebra, we don't have to write things down. But it's preparation for book six, which is similarity. So like AAA, angle, angle, angle. If three triangles have the same angles, then the sides, the corresponding sides of the triangle are in proportion. Right? We remember this concept? Okay, similar triangles. This is angle, angle, angle. Book seven through 9 are number theory. Books 7 through 9 are number theory, and we'll discuss his number theory. And this is the one section of the elements that is believed to be original to Euclid. All the other stuff was a compendium of what other people already knew. This is believed to be original to Euclid. And there's really beautiful stuff in there. We'll spend a little bit of time in those books. Book 10 is large. It's about all kinds of things, but largely it's about incommensurability. Things like the square root of 2 is irrational. So that's where you'll find, that's something people knew and worried about at that time. So where is it? It's in book 10. Okay, as we already know that subject. And then books 11 through 13 leave the realm of a flat plane and go into three-dimensional shapes. So this is solid geometry, culminating, and the entire, there's only 13 books. What does that say? That says 12. 13. There's only 13 books, and the finale is the construction of the Platonic solids. I'll explain. Culminating in Platonic solids. Namely the tetrahedron, octahedron, cube, icosahedron, and dodecahedron. Okay, and you'll know what all those words mean by the time we get there, and why they're the only that there are 5 Platonic solids and no more, and how Plato thought about them as this was the first attempt at a fundamental theorem, like an atomic theory. And he thought that these Platonic solids that you can prove mathematically are the only ones that exist. They're the analogs. These Platonic solids are the analogs of regular polygons. He starts with regular polygons, right? The very first thing of book 1, proposition 1 of book 1 is the construction of a perfect triangle. So Platonic solids, I'm getting ahead of myself. I can't help myself but tell you what Platonic solids are. What's a regular polygon but in 3 dimensions? What's a regular polyhedron? So imagine, what's an equilateral triangle? All the sides are the same. What's a regular n-gon? All the sides are the same and all the angles are the same. So now you say, okay, all the sides are the same, all the angles are the same, all the dihedral angles are where 2 faces meet, and all the faces are the same. So if you're going to have, 5 triangles meeting at every corner, at every vertex, what shape does that make? And what does that look like? Maybe I'll bring in some models so you guys can play with them. But he did all of this without 3D printing anything, and it's this wasn't original to him. These last chapters, the number theory really is believed to be original to him. Okay, so that's like a global overview of what's in the elements. So let's dive into book 1. Any questions so far? Makes sense? This is what I mean by it's a compendium of everything that was known. He begins with equilateral triangles. He ends with the construction of the icosahedron and the dodecahedron.
Like he stated that it was somebody else who came up with it.
He stated that it's due to Pythagoras, because as far as he was aware, it was to him due to Pythagoras. Oh, yeah, he gives. Let's see. So what I love about this website is it gives the entire. Maybe he doesn't say it is the Pythagorean theorem. So here's. Let's skip all the way down to proposition 47. And the statement is, in right-angled triangles, the square on the side opposite the right angle equals the sum of the squares on the sides containing the right angle. Okay, that's his, that's almost a direct translation of it. Does he have commentary? That's a good question. I don't remember if he has any commentary around it saying this was originally due to Pythagoras, at least as far as he knew. Now we know, of course, that it was known well before and in lots of other places. Yeah, I don't think there's all that much discussion. It really has the structure of definition, postulate, axiom, common notions, proof. Okay, good. Yeah, great question. So you see here, so proposition 47 is the Pythagorean theorem. Proposition 48, if in a triangle, the square on one of the sides is equal to the sum of the squares on the remaining 2 sides, then the angle contained by the remaining 2 sides is right. That's the converse to the Pythagorean theorem. And proposition 46, to describe a square on a given straight line. So the second he can construct a square, he uses it to prove the Pythagorean theorem, followed by the converse to the Pythagorean theorem. So let's build up to that. We'll get just, we're not going to do every single proposition. I want to go sort of step by step. There's a beautiful version, and just to show you, here's proposition 1 to construct an equilateral triangle on a given finite straight line. There's a beautiful version of Euclid that was given by a 19th century mathematician named Oliver Byrne. And Byrne's version is just beautifully illustrated. And so that's, but Byrne changes a couple of things. So I don't like it because he changes things, but I like it because he gives like, here's proposition 1, and it's on a given finite straight line. Can you see that, or should I make it a little bigger? You can see that. You can see that. On a given finite straight line, that's black, and you can sort of hover over it. Well, Byrne didn't have HTML. This is an HTML version of Byrne's thing to describe an equilateral triangle. And Byrne's version is you describe the blue circle and the red circle by postulate 3. We'll come back to what that is. Then draw the yellow segment and draw the red segment by postulate 1. Then this triangle, the claim is that this triangle is equilateral. Why? Because black is equal to yellow, black is equal to red, therefore yellow is equal to red, and so it's an equilateral triangle. Okay, let's go over all of that nice and slow and in some detail. Okay, this is just I'll put a link to this also on the page, and I've printed, although I think I somehow made several copies of page 1. Okay, so here's page 1. So let's go right into how Euclid's Elements actually starts. And we have to jump between Byrne's version, which is very pretty to look at, but is not historically accurate, and Euclid's actual version. So from the beginning, you've already seen this, Danielle. In Byrne. Here. Oh, yeah, that's a good question. I don't know why they chose to, do they say? I don't know. I don't know. Why? Yeah, maybe these are constructions and the others are theorems. Maybe that's why. Yeah. That's one immediate guess. I don't know why they chose. That's not original to Euclid. By the way, we really have no idea what's original to Euclid. The oldest surviving copy of the Elements it's an easy year to remember, is the year 888, Common Era. Okay, 888. So let's put a little note. Oldest surviving copy of the Elements is from 888 AD. Okay, yes. I don't know where it was discovered. It lives now in Oxford. This is located at no 888. So it's 1,000 years from us, and also 1,000 years from Euclid, roughly. Yeah. So it's about, but it's 1,000 years after Euclid. And when we look at Byrne and how much Byrne changed Euclid, granted, people call it Byrne's Euclid. It's just nice to look at, but you'll see immediately that he changes. How many definitions does he have? This is his list of definitions. It goes up to 35 definitions, whereas Euclid has 23 definitions. Okay, so he added a whole bunch of definitions. He changed some of the words. He changed the postulates. There are the 5 famous postulates. He's got 3 postulates, and then he goes to axioms. So this is what I mean by people mess with it. Hopefully people mess with it less in the first 1,000 years than they did in the next. Who knows? But this is, so we'll jump back and forth between what is believed to be the something closely approximating the original Euclid. There's an argument about whether these definitions were in Euclid, and maybe they were added in 300 AD CE. Elisa? Is where it was discovered? Where? Oxford did?
Written in Constantinople by Stephanus.
Okay.
Bought by and then a bishop had it.
I guess I should say Istanbul. Istanbul, Constantinople. You guys know it, yeah.
No, actually, so the owner was unknown until the 17th century.
Okay. With most of these things, like, you know, who really knows? But the versions that actually, so this version, I don't know the history of this 800 CE version, but that's not the version that people were working off of. There were Arabic versions, Arabic translations that were written in the year 1100 that were taken from Baghdad and translated into Latin in the 1300s. And you'll meet some, so there's some very important people in the history of mathematics who became famous by translating Euclid and giving an extra description of what's in Euclid and some extra discussions, things like this. Okay, so we'll come back to that. Definition 1. A point is that which has no parts. Okay, that makes sense, right? A point is just this. There's a point. It has no part. It has no length. It has no width. It has no depth. Definition 2. A line is a length without breadth. So there's no thickness to the line, an ideal line. By line, he means curve. The extremities of lines are points. Lines end. Line really means line segment, curve segment, and it ends in points. And a straight line, or a right line, but nobody says right line, a straight line is a line that lies evenly between its extremities. Okay, that's what a straight line is. A surface, yada, yada. So you watched the video discussion. What's wrong with this?
Like scale lines, like a circle.
You're getting much later. Yes, that's where this discussion ends, is with non-Euclidean geometry. But Allison.
So basically, if you say you have a line that's necessarily straight, it could look like that first one.
We will use the word line to mean a straight line, and we'll use the word curve to mean, yeah. So this is just like antiquated terminology. This is really curve.
Oh.
And the extremities of curves are points. And then a straight line, we don't say right line. A straight line is a straight line, is a line. Danielle? Yes. Exactly. What is a part? What does it mean to have a part or not to have a part? What is breadth? In the same way that axioms, why do we know we have axioms? Because you're going to prove some mathematical theorem in terms of some other mathematical fact, in terms of some other mathematical, and there's this infinite cascade of facts that are built on facts. And we said, no, we have to stop that. We have to cut it off somewhere. We have to have axioms. And from those axioms, we build our theory. In the same exact way, modern mathematicians realized you can't have definitions of fundamental objects. You can have a definition of an equilateral triangle, but not a definition of line segment or straight line or point. Okay, so all of this by modern terms is nonsense. Just cross it off. Okay, you must have undefined terms. A point is this undefined thing. Never mind what you can have a model of a point. Sure, you can have an idea of what a point is, but in rigorous mathematics, you cannot define what a point is, because how are you going to define it? In terms of what more fundamental object? In the same way that you're going to prove a theorem in terms of what more fundamental axiom. Okay, so there has to be a starting point, and that starting point has to be nothing. In the modern world of topology, we were having this discussion. What does it mean to be open? It doesn't mean anything. It's just a word we use, and we're going to build a theory. We're going to have axioms on how you can use open sets, and we'll build things on it. Nargis, what's wrong? The proper way to do this by modern standards is to say we will have undefined terms, point, line, and plane. And the question is, what can you do with point, lines, planes, and circles?
Point lines, planes exist.
There will be words called points, lines, and planes.
Just
Right. You can't. Because how do you justify? In terms of what else will you justify it? The same problem occurs when you try to give foundational definitions. Exactly. Exactly. That's exactly that same principle. Okay. So never mind that this is by modern terms nonsense, but there it is. A point is that which has no part. A line is a breadthless length, yada, yada. Some important definitions are definition 10. Let me come back to definition 10 and tell you why it's important. So let's skip down to the last definition, by the way. So definition 22, what is a square? It's a quadrilateral, a four-sided rectilinear shape. By the way, he talks about rectilinear figures in definition 19. Are those contained by straight lines? Trilateral or what we call triangle. It's kind of funny. Triangle is the only shape where we refer to the angles instead of the sides. Everything else is a quadrilateral. Pentagon, hexagon is about number of sides, not the number of angles, of course. It's the same. Anyway, so that's what a rectilinear shape is, as we already know. An equilateral triangle is a three-sided triangle where all the side lengths are equal and all the angles are equal. Scalene triangle, yada, yada. A right triangle is that which has a right angle. Obtuse triangle has an obtuse angle. Acute angle. What's a square is both equilateral and all right angled. All the sides are the same. All the angles are the same. That's what a square is. Definition 23. A square does not refer at all to parallelism. It has nothing to do with parallel. It turns out that the sides of a square are going to be parallel. But it's only definition 23 where we get to something called parallel lines. What are parallel straight lines? Parallel lines are two lines in the same plane which produced indefinitely. If you were to continue them as far as you want in either direction, they will never intersect. They do not meet in either direction. Okay, that's what parallel lines are. According to Euclid, that's the last definition that Euclid puts down, and then he goes to the postulates. Let's zero in on the postulates. So unfortunately, and you can read Byrne's version of this, and there's some good stuff in here. If you have a quadrilateral, here are the diagonals of the quadrilateral. Here's a triangle whose three sides are equal is said to be equilateral. Okay, so he's moving around where this definition lies, but this is what it means to be an equilateral triangle. The three sides are equal. He goes into right triangle, obtuse, scalene triangle. A four-sided figure has all sides equal and all angles right is called a square. This, for Byrne, is definition 30. We really shouldn't be doing Byrne. Someone should make a really beautiful version that looks like Byrne, but is the original Euclid. Okay, I don't have time for that kind of thing. What he says is an oblong, what we would call a rectangle, is something that has right angles, but not all sides necessarily equal. And finally, at the end, he gets to the same punchline. Parallel straight lines are those which are in the same plane, right? I can have lines that don't intersect but are not in the same plane. So if we're in the same plane, if they're not parallel, then they're going to intersect somewhere. If they're parallel, then no matter how far if there's segments of lines, but I can extend segments of line. And if I do, they still will never intersect, no matter which way I extend them. Okay, does that make sense? Postulate 1, let it be granted that a straight line may be drawn from any point to any other point. You give me a point A, you give me another point B, I can put a straight edge there and draw the straight line from A to B. By line, I mean line segment. Okay, that's postulate 1. And that's the same as Euclid's, to draw a straight line from any point to any point. Postulate 2, to produce a finite straight line continuously in a straight line. What the heck does that mean? If I'm given a line segment, exactly, let it be granted that a finite straight line may be produced to any length in so if I'm given a line segment, AB, I can put that straight edge right up to AB and extend it a little bit farther if I so choose. Okay, so this is extending, producing a straight line in another straight line. So if you've already drawn that straight line, you can make it longer, as long as you need it to be. There's no discussion about infinity. There's no such thing as infinity. Everything is being drawn on one piece of paper. You can extend a line segment if you need to, if you've already drawn a bit of it. You just hold up your ruler, not ruler straight edge. You hold your ruler, your straight edge up to the length you already measured, and now you can measure out something a little bit longer. Okay. Postulate 3, may be granted that a circle may be described with any center and any distance from the center. You give me a center to a circle, you give me a point on the circle, I will be able to draw a circle with center O and going through the point A. Okay, that's postulate 3. Let's see what Euclid says. Euclid says to describe a circle with any center and radius, exactly what a compass does. Here's a funny postulate. Postulate 4, that all right angles are equal to one another. The heck is he talking about? 90 degrees is equal to 90 degrees? Why do you need this?
Segments are.
That's a good guess. That's a good guess. It's not about the line segments. And this is an instance where Byrne goes off the rails from Euclid. He defines a bunch of axioms. He separates things into postulates and axioms. And right here, his axiom 10 is what I would call postulate 4. Oh, sorry. No, that 11 right here, that all right angles are equal. All right angles are equal. We have to go to a definition of right angles. So that definition is right here, definition 10. When a straight line standing on a straight line makes adjacent angles equal to one another. So let's look at that. Let's see, where does Byrne have it? It should be 10. Here we go. When a straight line standing on another straight line, if I have one straight line and I have another straight line, I'm going to draw this in a funny way just to make the point. So that the two adjacent angles happen to be equal. They don't look equal. I drew them like that on purpose. But if the adjacent angles are equal, then we say that the lines are perpendicular and that the angles are right. Okay, this is what it means to be a right angle. If the two adjacent sides, when two lines cross, are equal. Here's Euclid's problem. What if you have another pair of adjacent angles that are also equal? And again, I'm drawing them not equal just to illustrate the point, Elisa. No, he says nothing about, there's no degrees. There's no discussion of degrees at all. So he gives a definition of what it means for a line to be straight, but that definition is nonsense. Because it's defining, what does it mean to be straight? So you just declare the existence of things called straight lines. And we're going to deal with them, whatever they may be. The rules of what you can do with straight lines are what's important. Given 2 points, you can produce a straight line between them, straight line segment between them. Given a straight line, you can extend that straight line. Well, that's what you can do with them. What it means to be straight, we're going to be agnostic about that. But here's Euclid's problem. He's going to call this situation a right angle. He's also going to call this situation a right angle. He has no way to compare when two lines intersect and those two lines also intersect with adjacent angles equal. How is he going to compare one situation to the other? What's he going to do? He's going to say that they are equal. He's going to declare them to be equal, and that's what postulate 4 is. Postulate 4 is that all right angles are equal because of the way right angles are defined. Given he does a masterful job. Again, these definitions maybe were added later, we don't know, but he does a masterful job of zeroing in on the key issues. Nargis. That's right. Exactly right. There's no notion of 90 degrees. They're just right angle means adjacent angles are the same. There is a notion of equality. That's it. So if a line cuts another line so that adjacent angles are equal, we're going to call that a right angle. The problem is some other line might cut some other line and again have adjacent angle equal, and I don't have a way of comparing these two. Postulate 4 allows me to compare those two. Okay, so that's what this is doing. This postulate 4, that all right angles are equal to one another. And you see what postulate 1 looks like. To draw a straight line from any point to any point, yes, of course. To produce a finite straight line continuously in a straight line, yes, of course, you can extend it. To draw a circle, given a center and a radius, yes, of course. All right angles are equal to one another. Why does that even need to be there? Oh, okay, fine, I see. And the obvious postulate 5, that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines produced indefinitely meet on the same side in which the angle is less than two right angles. Right? Everybody got that? It's obvious. The hell is he talking about? Elisa. That's a good question. So It's not, I wouldn't say that each postulate is a precursor for the next postulate. The postulates are kind of independent of one another. But certainly he saved postulate 5 for the end. And as you'll see, fully half of book 1 does not use postulate 5. Only refers to the first 4 postulates. The second he starts using postulate 5, he uses it for the rest of the book. And he will definitely need postulate 5 of parallel lines in order to be able to prove the Pythagorean theorem, because the Pythagorean theorem is not true in other geometries.
Based off the picture that was used in the other definitions that you were showing us,
Yeah.
it would, one can explain postulate 4 with postulate 3 regarding circles, meaning like.
How?
Well, if you say like it's a fourth in a circle, and instead of thinking about a right angle
Yes.
as like an angle, thinking about it as a circle. And the reason I was saying that is because in postulate 3 that was described in the other example you were showing us, they showed half a circle.
You mean in here? That's just trying to show this angle and that angle being the same. So why, if these two angles are the same and I go somewhere else, why are those the same? You've moved the circle somewhere else, even if it's the same circle. A quarter circle, why does a quarter circle have to measure the same angle at one place or another? Euclid felt, we can argue about whether postulate 4 can be proved from the others. What people zeroed in on is postulate 5. Look at postulate 5 again. For some reason, Byrne puts this as his last axiom, but here it is. If 2 straight lines meet a third straight line, so as to make the 2 interior angles on the same side less than 2 right angles. Let's really read this. Let's really read this. If a straight line, I'm just going to copy all of this text. Copy, and let's parse it bit by bit. I'm just going to paste it here. Oh, come on. Can't you make it bigger? There we go. Nice and big. Okay. So 2 straight lines. If a straight line falling on 2 straight lines, here's one straight line, here's another straight line, and here's my third straight line. Okay. So if a straight line, that's this, falling on 2 other straight lines, that's these 2, makes the interior angles on the same side less than 2 right angles. So if this is alpha and this is beta, whoops, it's supposed to be a beta. What he's saying is alpha plus beta is less than 2 right angles as 180 degrees. Okay. If a straight line falling on 2 straight lines makes interior angles on the same side less than 2 right angles, then these 2 straight lines, if produced indefinitely, I don't have enough room to produce them far enough, will meet. And not only will they meet, they'll meet on the side. So they're supposed to meet, and they're supposed to be straight lines. They will meet, and they'll meet on the side where the angles add up to less than 2 right angles. So where to produce them indefinitely is in the direction, because you could also produce them indefinitely over here. I'm not saying they're going to meet over there. I'm just saying that they will meet if alpha and beta adds up to strictly less than 2 right angles. So he doesn't call it 180 degrees. He calls it 2 right angles, a right angle plus another right angle. Then they're going to meet, and they're going to meet on the side. So it's the unparalleled postulate. It's not the parallel postulate. It's the unparalleled postulate. 2 lines are not parallel. They will intersect in the plane if these 2 interior angles add up to less than 2 right angles. And you can start to imagine why people had a problem with calling this thing an axiom, a postulate. You have these 4 like half sentences and then an entire paragraph. This should be a theorem. This isn't a postulate. This is a theorem. Laura.
Like, isn't this sort of implied by the postulate that defines perpendicular lines? I don't know.
That's a great, because you want to, how so?
That's, I suppose it's what? I don't know. I mean, in my head, some combination of postulate 10 and axiom 10 and axiom 23 kind of implies this. But assume you can't do that.
Yeah, since we've already, you already watched the video about non-Euclidean geometry, I can jump the gun and show you why not. Okay, so maybe what you're thinking is that, well, what is a parallel line? What does it mean to have parallel lines? You take a right angle, right? Like you go along some distance, you take a right angle, you take a turn, you're going west, you turn so that you're going exactly north, and now you have another right angle over here, and you turn now so that you're going exactly east. How can that not define two parallel lines?
Yeah.
Right? Everybody agrees that there's no way, if you make two right turns, that you will not have two parallel lines.
In the non-Euclidean plane, is that what it was?
Who says, in fact, this is not true in the world that we live? No human beings have ever experienced parallel lines. Parallel lines are lines that if you extend indefinitely, continuing to be straight, they will not intersect. If I start going exactly due north, and Lori, who's 10 feet from me, also starts going exactly due north. Let's see. North, I think is that way. So we both start going exactly due north, right? And we're separated by right angles. Like if Lori were to come right here, and we're at right angles to one another, and we both go exactly due north, what happens? We meet at the North Pole. Right? We meet at the North Pole. We get in, right? You can have on a sphere, you can have triangles that have three right angles. A right angle here, a right angle there, and maybe we meet at the North Pole at a right angle, following straight lines. These lines that when I said you go east, by the way, you know how when you fly from if this is Florida or something, here's Mexico, you fly from New York to London. And you know the plane goes like this to make sure that you like stay near land, maybe Greenland's over here or something. Is that why they do it? No, why? It is the shortest path. That's what geodesics means shortest path. That is what the geodesic, if you actually look on a globe and you pull a string taut from New York to London, this is the path that it will trace. It's just that we've flattened out that picture. There's no way to flatten out that picture without distorting the distances and what these lengths are. So when people say, well, you fly exactly due east, you can't fly due east without turning the wheel. It's not it is a wheel, but you're turning the whatever on a plane. What's it called? Blanking on the name. Okay, whatever. You without constantly turning. And the way to think about that is, okay, maybe here it's not obvious, right? Actually, if you're on the equator, then you can fly directly east and just keep the plane going straight. Think about what's happening at the North Pole. If that's the North Pole, and I want to go exactly due east, I constantly have to be turning to stay at the same line of longitude or latitude? Longitude around the North Pole, okay? So going east is not a geodesic. It's not a path of least distance. You have to be constantly turning to go east. Okay, we jumped the gun a little bit, but so Lori, does that answer your question?
I know it's not really a useful question.
It's a very useful question. It's a question that haunted us for 2,000 years until we finally got to the answer. And part of the answer was giving up on definitions of what a line is. Eleanor.
That like latitudes and longitudes are parallel and equidistant.
Yeah, we call them the something parallel, right? The 28th parallel. They're parallel in the sense that they don't intersect, but they're not straight lines in the geometry of the sphere. Those are the words we use, but that doesn't mean that those words. So it's because of the Mercator projection. When you take the Mercator projection, which is the standard way to people look at things, in that projection, they're parallel lines, but they're not. There are no parallel lines on the sphere.
Like the equator.
Yeah.
This
Yeah. Those lines are straight lines. If these are latitude, longitude is this way. Let's get these because I confuse these also. There's these lines, and those lines all intersect at the North and South Pole, and these are the longitude lines,
Meridians.
the meridians. And then these lines, the way that people draw these are not straight lines. And the way you can tell is there's one that circles around the equator, circles around the North Pole, which obviously if you want to go around, you have to keep turning. But sorry, did I, before we go to Nargis, did I answer your question? And so these, now you can't tell what I'm pointing to. Longitude are these, and then latitude are these. For two lines to be parallel, first they have to be straight. And those lines aren't straight. Because you can't fly without turning and stay on those lines. Nargis. The-
So it looks parallel when you like look at it?
Yeah, there's a very, very good reason to use the Mercator projection. It's just that there is no, short of just keeping a globe around, which people do, there is no way to turn that globe into something flat without distorting distances, angles, something. Mercator does actually a great job because the angle at which you want to travel is the angle that Mercator says to travel along. It's just that what looks like a straight line in Mercator is not really the path that you will literally travel along once you start moving.
It's like distorted by the having to draw it on a piece of paper.
Yes, by the geometry, by the inherent geometry. This is something that Gauss really figured out. Elitsa and then Cindy.
If you took one point on one of the circles that you drew, and another point on the circle, those points,
On the longitude or the latitude? Or just anywhere? Or just on the sphere?
um,
On the latitude, okay? So I'm going to take a point like right there. One right below it, yep.
like those two circles in space won't intersect.
But they're not circles because circles, well, okay. Those two circles will not intersect, correct? Just like in the plane, this circle and this circle does not, these two circles don't intersect. So what?
Yeah, so is there, we're not engaging with it, meaning because so then there, it seems to be that there's something. If we're talking about intersection and lines, and the lines have to be parallel in order to, lines need to be, it needs to be a line for it not to intersect, but those aren't lines, but yet they're not intersecting.
Those aren't lines. They're just circles.
And they're also not intersecting.
Yeah. Yeah. We have no problem with circles not intersecting. Cindy and then Amelia.
Explain what's going on here. So the thing is, a lot of like this kind of like globes of like sailing navigation that happens in the 15th century, and a lot of it is actually based on Euclid's elements. And they borrow, well, it's not Euclid's elements, but they borrow a lot of the same language and definitions, but then rework it for navigation. So they have things like parallel circles instead of parallel lines. And you should not be comparing these directly, because you should think that's a whole separate set of math almost, because they have their own axioms and definitions. And this is going to drive you insane if you try to think parallel lines here and then parallel line there.
Yes. Spherical geometry is not a subject that's directly addressed in Euclid's elements, and certainly not from the point of view of as this is as valid a geometry as the plane geometry.
Okay.
Yes.
And then we wrote it in terms of sailing and navigation, and that's why it'll look very similar terms, but they're
Yeah.
not exactly the same.
And sailing's also notorious for having you have to double your vocabulary if you go sailing. There's the port and the bow and the stern and the hull and lines. By the way, you know what lines are in sailing? The ropes. You never say rope, you say line. Yeah, there's a line going this way and a line going that way. Because they're anyway. Amelia.
They can't really be parallel because they're not going into the same direction. So if you were to think about like, I guess like a west pole, they would intersect.
That's right. So even here, if I I don't know, if someone at the equator starts going directly east and I'm on the same longitudinal line, but just in New York, and I start going east, then it's true that we will intersect, well, somewhere. In fact, we'll intersect twice. We'll intersect there and we'll intersect at the antipodal point. So on a sphere, if you've heard of the parallel postulate being that a circle that for a line there's and a point not on the line, there's exactly one line parallel to it. That's another version of the parallel postulate, an equivalent version. On a sphere, that's not true. There are no parallel lines, and in hyperbolic space, there are infinitely many parallel lines. So, okay, we'll come back to all of that. Emilia.
Total like disregard all of this.
You know, I had some sympathy for the flat Earth people because how do you know? Do you know that the Earth is round? How do you know? You know, NASA says, you know, the man says that they're round, that the Earth is round. There are thousands of proofs that people can and do. There are thousands of observations that one can make and should make. And this is why I lost my sympathy for the flat Earth people, because they're not, you know, if someone says, you know, like, how do we, let's go back to first principles. How do we really know? And then you tell them those thousand things and they go, no, but how do we really know? And you're like, okay, you're not serious, right? You're just you're just wasting everyone's time. So I love when someone wants to learn something from first principles. I hate when you show them those first principles and they go, no, but how do you really know? It's like, okay, there's no, now you're wasting my time. So I initially, when I first engaged with these people, had some sympathy for them because I like first principles. And then I realized they were not interested in science. They just wanted to be contrarian. Okay, so do engage with first principles. Yes, question everything. And then learn what's going on and decide for yourself. Here's the problem with flat earthers. You tell them, what is the evidence that will convince you that the Earth is round? And I'll give you 10 experiments that you can do to convince yourself that the Earth is round. And they say, no, that's not evidence. And you're like, okay, so what is the evidence? If there is not something that can falsify, if there's not an observation that can falsify your theory, this goes across all of science, social science. If there is not a way to falsify what you think is true, then you have a religion and not a science. Tell me how to falsify this. Okay. Yeah, and of course, I talk so much that we're out of time. I'll tell you what postulate 1 is, and then proposition 1. So we get from the postulates to the common notions. Common notions are things like, if two things are equal, if A is equal to B and B is equal to C, then A is also equal to B. A is also equal to C, right? That's a common notion. If two things are equal, and let me write some of these common this is what Byrne calls axioms. Let me just write them over here before we get to postulate 1. Two things are equal, so if A is equal to B and B is equal to C, these two imply that A is equal to C, things like this. If equals are added to equals, so if A is equal to B and C is equal to D, then A plus C is equal to B plus D. Things which coincide with one another are equal to one another. The whole is greater than the part. So if I have a length and I have a length inside of another length, then the smaller length is genuinely smaller. These are the common notions. And then we get to proposition 1, which is where we'll pick up next time, which is to construct an equilateral triangle. So think about, here's your little mini homework. Think about, if I give you a little segment, given a little segment, how would you construct an equilateral triangle with that being one of its sides?